My last video was about the horizon tube test, and I worked out the math from the globe point of view, from the globe Earth model, and I didn't do the flat Earth model. Let's do that now. So the question is, does the horizon really rise to eye level on the flat Earth model? This comes back to Antonio Subirats suggested that we look through a tube, and he correctly points out that on a globe, if we're looking through a tube, we'll have to angle it down slightly in order to see the horizon. And if we've angled it down on one side, then if we look back up through the tube, it'll be angled up. And in the previous video, we looked at what the math was for that. But then he shows here that if it's flat, the angle to the horizon will be horizontal. But as you can kind of see in the diagram, he's got the tube is up above the horizon a little bit. So wouldn't it have to be angled down ever so slightly to hit wherever the horizon ends? So let's take a blow up look at this. Again, this is not the scale. This is all blown up to exaggerate so that we can see what we're talking about. So here's the Earth, nice and flat, and we are some observer up above the Earth somewhere looking at the horizon. Now here's the horizontal, but the horizon presumably is where the Earth ends, where we don't see anything more. This is the Earth down here, and this is sky. So if the Earth ends there, then we must get sky right there. Okay, so there's some alpha, some angle below horizontal to that point. And where is that point? If our height is this high, h high above the Earth, we need to know how far out is it to that point, and I'm going to call that d. And then we'll just have an arctangent to tell us what the angle is. So I've got here your standard flat Earth map, which is just the azimuthal equidistant projection. So in this map, we'll put the North Pole in the middle, and the South Pole gets all stretched out all around the outside. Critical Think did his experiments in Byron Bay, Cape Byron. It was approximately there, give or take, on the edge of Australia there. And if we're going to answer the question of how far away is the horizon, and we say this is the horizon, then we'll need to know not only where you are on the Earth, but then also which direction you're looking, because if you're looking south, that's how far away it is, but if you look any other direction, you can see the distances are going to vary quite a bit. It occurs to me that if we're able to measure any angular drop to the horizon from that point, then we could actually estimate the size and shape of the outer rim using this technique. So let's see if we can make that happen. I've never gotten any hard numbers for the flat Earth, but the radius of the globe Earth is supposed to be this size, and I have heard that the flat Earth map is supposed to have distances that are the same as on a globe. We won't get into the fact that that's not possible, but I'll try my best with it. That would mean with this radius for the globe, here's the circumference of the globe, and that comes out to about that, 40,000 kilometers, give or take. And so if distances are supposed to be the same, my interpretation of that is that this distance across the flat Earth is the same as the circumference of the globe Earth. So that would give me something to work off of. Okay, so now which direction is Critical Think looking? He's looking down this walkway here. You can see the lighthouse over here and these orange roof buildings there. And here's something I got off Google Maps. Check it out. Looking that same direction, and you can see the same buildings. There's the lighthouse, and it shows me pointing south. So I surmise from that Critical Think was looking approximately south. That's good. Okay. So where is Cape Byron and the lighthouse? It's right there. The interesting thing we're going to want is how far south is that? Okay, we're here. Here's the size of our flat Earth. So I want to know, how far is that? Well, the radius of this thing is half of this, 20,000. So that means out to the equator is half of that. And from the equator to Cape Byron is that much based on the latitude we just looked up. And then that leaves out to the rim, from Cape Byron out to the rim is something like 6,800 kilometers, something like that. Okay, so taking those as an estimate, plug it in. And what do we get? We see from the observation height in Cape Byron of 97 meters, the angle is very, very small, 0.0008 degrees. Okay, how about going the other way? Going the other way is actually smaller, so it's much farther out to the opposite rim. So when critical think looked the other way, we got an angle of 0.00016. So substantially smaller, but they're both so small that I wonder, can we even measure that? Can we even consider that an angle? Or perhaps can we agree that the horizon does always rise to eye level? It's not technically eye level now, is it? But dang if that isn't close. Let's try some other places. Here are those same numbers from Cape Byron, looking south, looking north. How about Pikes Peak, for example? Pikes Peak is very tall, and you can just drive up to the top of it. So it's a convenient place to take a look out and set up your tubes and take a look. This is what you should get looking southward from Pikes Peak. The number is a lot larger. You get a much more angled drop to the horizon on Pikes Peak, but still it's hundredths of a degree. We're talking less than 2/100ths of a degree. So still pretty small. How about an airplane? Just to pick a location, we'll go back to Cape Byron and we'll go up to altitude and look south. So look south out the window and take a look. Now we'll see 0.08 of a degree horizon drop. So the horizon does not perfectly rise to eye level. It does drop as you go up in altitude, but only by these, look at these tiny little numbers. The biggest we got up in an airplane, 0.08 of a degree. Let's take one more look at that tube test. If you recall with the tube test, we aim the tube at the southern horizon and then we look back up through the tube, and then that'll sort of magnify the effect a little, because on the one side we are not only above the horizontal, but the horizon is below the horizontal. So the total angle is the sum of the two. And for the Cape Byron observation, we're expecting something like that. Just shy of 1/1000th of a degree. So can we see that? Will we detect that? We usually say that the resolution of the human eye is something like 1 arc minute, and 1 arc minute in degrees is there. And unfortunately, that is approximately and is over 10 times the angle that we're trying to measure. So no, we won't be able to see that with the naked eye. We could measure it with a theodolite though. So if you were serious about this and you wanted to get really precise, get yourself a theodolite and measure. Yeah, you could get down there and say, aha, the horizon did not quite rise to eye level. But as far as you're going to be able to tell with the naked eye, yeah, on a flat Earth, horizon's going to rise to eye level. Okay, hold on. At some point, hopefully somebody out there noticed that you cannot see out to 6,800 kilometers. There's just no way that's going to work out. There's too much haze in the air, or just whatever. You're never going to see that far. And yeah, that's true. But this whole video is about, can you see, does the horizon rise to eye level, right? And to get the horizon to rise to eye level, you need the biggest number here you can get. So I wasn't the one saying the horizon rises to eye level. I'm trying to help you out here. Okay, let's go the other way. How far can you see? Can you see to 443 kilometers? If you can see out to 443 kilometers, then the eye level the horizon rises to is about 100th of a degree. Or maybe you can't see out that far. Maybe you can see to 120 miles, in which case this is kilometers of that. Now it's almost 300ths of a degree. The horizon would be almost 300ths of a degree below your eye level out at 120 miles. Interesting. The closer in that horizon appears to be, the lower the horizon appears to be. And this is with flat Earth calculations here. So maybe the horizon doesn't rise to eye level. Maybe the reason we got this measurement is because the horizon didn't rise to eye level. Maybe the horizon appears to be 3/10 of a degree below eye level because that's as far as you can see through the haze. Maybe. How far would that be? Well, if we can see out to 3/10 of a degree and we're at 97 meters, then all we have to do is solve, and we're going to come up with about 18,500 meters, or 18 and a half kilometers. Could we be seeing out to 18 and a half kilometers? Is that maybe how far we're able to see in this picture? Could that maybe be 18 and a half kilometers right there? Let's see. If that's the case, then this line doesn't represent the real horizon. That's just the apparent horizon. That's just where we can no longer distinguish between the water and the sky. And the real horizon is somewhere above that. Where would that be? Well, the center line that the tube is looking at right now is right there. And remember, that was 2 angles up above the horizon. So this would be 0.6 degrees. So the middle right there, that's our 0 line. That's where the horizon is supposed to be. The flat Earth horizon must be at the center line, and this bottom line isn't the real horizon. That's just the last point you can see through the haze, right? Okay, see, now that could kind of almost work, right? We have this measurement. There's no question that's 0.6 degrees above the horizon. That you just let go of that, right? That's 0.6 degrees above there. The horizon didn't rise to eye level. Simple as that. Why not? Well, if it were flat Earth, of course the horizon's expected to be there, but only if you can see out to 6,800 kilometers. If you can only see 18 and a half kilometers, this is where your horizon is, right? So you can possibly still hold on to that flat Earth, but you've got to let go of the horizon rises to eye level. The horizon doesn't rise to eye level. You're looking at it right here. So what if 18.5 is just the end of the haze? Could be. You're going to need to look closer at pictures like this and really answer, is that haze right there? You're going to have people saying, no, that's not haze, that's sky. There's no water here. You'll have to look at that and be honest about it. Look at it. And you might want to look at this thing here. This little piece of island right there. If that is more than 18 kilometers away, then you're going to have problems with this. So there's how you can use math to check your assumptions. Does the horizon really rise to eye level? What does the math say? What do you expect to see? Why do you expect that? Can you check. You can use the math to check your assumptions and see what's really going on. And then compare that with reality. Make an observation. Compare that with the math. Go back and forth. If the math doesn't agree, look for an error. Is there an error in your experiment? Find possible alternative explanations. We can explore all these things, but only if we do it honestly and fairly.